Hello friends, welcome to AMT, Automotive Embedded Technologies. Here I would like to introduce myself. My name is Sai. I have 12 years of experience into automotive embedded systems and I would like to share my knowledge that I have gained so far from past 12 years in terms of vehicle architectures grown from different stages, software development techniques, industry standards, communication protocols used, and various latest functions that has been integrated into the passenger cars or like ADAS features, I would say. And there are several evolutions happened in vehicle architecture from past decades. And I would like to discuss this in further slides to understand what kind of architectures were grown from past years and what are the basic components used in automotive embedded systems. So first we discuss about the basics of automotive embedded systems and how this has grown from one step to other step in a way. So the main basics of automotive embedded systems contains electronic control units where each control unit has its own specific job to deliver a function or a feature to the end user like a seat belt functioning or comfort driving or safety or security of the systems. And of course, there might be several kind of ECUs in each vehicle. Around 30 to 40 electronic control units might be present in the older architectures are communicating together using CAN or Ethernet communication protocols and delivering the functions to the end user for the comfort and safety driving on real roads. And coming to ASIC, application-specific integrated circuits are the intermediate boards of the system that has been used to enhance the data between the main electronic control unit and the remote sensors, what has been used for explosion of airbags or for the activation of airbags or emergency braking or ultrasonic sensors used for parking guidance or different kind of cameras used for 360 degrees view and so on. And coming to sensors, we have several sensors in vehicle for tire pressure monitoring system, for the door intruder detection system, or for emergency braking system like a radar or lidar, and etc. Coming to actuators, there are several actuators in vehicle architecture which are associated with a small motor control units to control the door locks or different kind of actuator devices for several controls in the vehicle. Coming to safety and security of the systems, we have several standards in automotive. So for safety, the main standard followed is ISO 26262, which talks about several safety guidelines to be followed during the vehicle drive and to provide a comfort and safety driving to the driver to not have major impacts to the environment as well as to the car user. And coming to security, the more important is um, to protect the data from vehicle communication control units to the outside world. For example, our daily life, we have our mobiles or other devices connected to the vehicles always, and where our personal data as well as vehicle data has been shared between our devices, what we are using personally, as well as the vehicle control units has. So this data can be hacked and can be manipulated from outside world by hackers and then get control of the users, peripheral devices or the vehicle electronic control units and maybe a loss if there is a big hack happens during the security breach, and this will lead to damage to the vehicle user as well as vehicle as well as the environment For this, there is a standard in automotive called ISO 21434 has been come up with several guidelines to be followed in terms of product development, ECU development, software development, testing, and etc. And we will discuss about these standards in upcoming videos. Coming to system engineering. System engineering is a major topic and it's a wide topic has been used across the product development, has several rules and guidelines to be followed to develop a single concept of a future, any of the future which is coming out of a vehicle has been elaborated from the concept phase in different stages to monitor the requirements, to monitor the development, to monitor the testing, to monitor how this has been working in a test bench or it has been working in a vehicle or how the experience is with the end user with several functions, etc. Coming to software development, and we have several the techniques and technologies followed during the software development phase of past decades. I would say there was no specific standard in the initial stage, and we were using standard communication protocols like embedded C or embedded C++ with several tools to test our software developed for the coverage or to find the bugs or etc. And later stages, there has been a specified standard called AutoSAR architecture has come up with several ideas and several rules and regulations to be followed during the development of different kind of software development modules. And this has been divided like an application layer, basic software layer, microcontroller layer, and hardware abstraction layer. And also this has a quite relation with OSI layers of the standard ISO. And then this has been evaluated later from AutoSAR, from basic AutoSAR to adaptive AutoSAR, where we have more enhanced features in terms of software configuration, integration, development, reusability of the components has been enhanced so far. And we will discuss about these details in upcoming videos based on each topic. And if you come to testing and automotive standards, so there are several kind of testing like bench testing, component testing, system integration testing, vehicle testing, and on-road testing. And for this, there are a lot of standards has been involved. And if the testing outputs are aligned with the standard guidelines which are given by the automotive industry, um, uh, standard vehicle, um, I would say, at the safety ratings providers, like for examples, NCAP rating and etc., where the vehicles got so and so rating, so that the vehicles are safe and secure to drive on real roads. Has more technologies involved during the vehicle development, I would say. And let's go to next slide. What is EE vehicle architecture? So the vehicle architecture mainly contains different kind of components. Like if you see here, we have the communication protocols like CAN-FD or Ethernet or I2C or SPI has been used between different sensors or actuators and ECUs. Coming to other issues, if you see, we have June 1, June 2, June 3, June 4. There are several regions in car has been divided and are connected to the peripheral sensors and ECUs to deliver their job for comfort, safety, and secure driving. And if we come to sensors, as we just spoke before, we have radars, cameras, lidars, and several other sensors which might be involved, may not be in car, but in also trucks and heavy duty vehicles For example, diesel particular filter, for example, a different kind of sensors based on the trailer and truck parts of different trucks has been involved in the vehicle architecture. And I hope you go through this message and understand the basic things of how the vehicle architecture is. And coming to next slide, we have several types of stages in vehicle architecture development, I said. So the first one is the basic architecture or multi-bus gateway architecture, where if you come to this part of architecture, this was the basic architecture has been followed from past decades, I would say, and the industry now is working towards the domain control architecture, also the zonal architecture, where we need these architectures for specific reasons. These reasons we are going to discuss in upcoming slides. Coming to the basic architecture, so we have a gateway ECU and we have each peripheral ECU and are connected to different small ECUs or sensors communicating in between and are together communicated on a single network, also here, and are only depending on one communication protocol. If you see these black lines, the black lines are connected either CAN or CAN-FD. So we are just using CAN or CAN-FD protocol to communicate between gateway and different ECUs. Also ECUs connected internally together has a complex network, I would say. Also this needs uh, more cost, more complex, and less efficiency in terms of power distribution, in terms of data distribution among ECUs. So the CAN or CAN-FD communication protocol just provide very minimal data rates, speed, as well as the content of data bytes to be transferred between different ECUs. And that's the reason there is a need of moving to functional domain controller architecture, as we see here, and where we have also communication with the clouds outside of our car. We have a specific cloud that provides some features to the car, as well as software updates and so on, where the ECUs are connected together using different communication networks, I would say, not just CAN or CAN-FD. Also we can see there is an Ethernet communication and other LVDS communications are happening between different kind of peripheral sensors or actuators like cameras, and we may use LVDS interface. And for CAN-FD we use between different local ECUs which are delivering specific functions in vehicle. And Ethernet is a major communication protocol used between different high computational units to share more data between the gateway as well as main control units of the car, where they are getting data from other ECUs on CAN and then sharing over Ethernet for the speedy communication, also for the efficient communication between different parts of vehicle. And here if you see, one set of ECUs connected on Ethernet and one set of ECUs connected on CAN and one set of ECUs connected on Ethernet based on the safety and security of the system. And this has been designed like this for more comfort and safety driving on real roads. And coming to zonal architecture, if you see most of the communication protocol we used either is CAN, FD or Ethernet. So I think most I see Ethernet is more used here for more speedy transmission of the data. Also more amount of data can be transmitted between different ECUs along with the zonal control units. As you see in the green box, here it is used as a green box as the vehicle has been divided into several zones and zone controllers has been established there for more computation of the data which is coming from the peripheral ECUs or sensors directly to the zonal controllers. And then we have a centralized computing system connected to these zone controllers as well as external ECUs indirectly, and then sharing data to the external world for different kind of software updates, and various other features of the vehicle, I would say. Like we have all of like um, entertainment systems and so on. Maybe a question comes: why this growth is required like this? In current trends, we have different aspects in automotive embedded industry, like autonomous driving, safety and security, electric vehicles, connectivity, computation, artificial intelligence, sustainability, and cybersecurity. To achieve several trends of this automotive sector, we need more computation, we need more data processing, we need accurate data processing, we need more speed in data processing, and we need more computation, as we just speak before, that we need more efficient system and speedy transmission of the data in between the systems for more safety and security. For this, we need the architecture topics what we discussed before, how the growth from classic to domain and domain to zonal control units. I hope you understand the basic here. And coming to autonomous driving, how automated vehicles works. So we have several sensors and units established in car, kind of cameras, lidar, radar, and GPS units for tracking, for knowing any kind of objects in front of or in the surroundings of the car, either maybe short range or long range or mid range. So for short range we go for lidar, for long range we go for radar sensors, and for the pictorial uh, understanding of the environment, we go with the cameras. Maybe we go with the 360-degree cameras, which are installed in different directions of the cars to understand the environmental dynamics. And here, if you see this picture, cameras, if you see cameras, we have a rear camera, we have a front camera here, two cameras here, and one in the mid of the car to see the frontal view of the driving. And for the rear view, we see the rear view of the driving. And then the other two cameras installed might be in the mirrors to get the 360-degree view of this car while uh, parking the vehicle. Coming to lidar, we see the lidars are, if you see here, the lidar in green color has been connected here to see the blind spots as well as the nearest objects to be detected in the corner sides of the vehicle, and to detect them as soon they arrive in the region, and then perform a braking or alert to the driver to go ahead with the um, drive with a minimal speed. Coming to radar, if you see here, radar has been established here as a sensor, three sensors to detect objects which are coming in the long range, and these are mostly used in adaptive cruise control feature to detect different kind of cars or objects in front of car and adapt the speed according to the target vehicle to the ego vehicle. And coming to the GPS unit, we have been an established GPS unit in the vehicle for the live monitoring or speed monitoring in terms of local navigation maps and etc. And coming to next slide, we are more talking about safety and security from past slides. So why this safety and security is required and from where this is. For example, if you see here, there is a small connectivity between automotive industry safety culture and information technology security culture. And in between how the autonomous vehicles are indulged. The safety of the vehicles are basically local to the vehicle. I mean, internal faults of the vehicle are major reasons of the safety in the vehicles, I would say. Coming to information technology, almost all we can see every car now has an external connectivity like a Bluetooth or Wi-Fi or connected to the service provider provides several functions or several updates on the softwares like how we are receiving the software updates in mobile. So here more information technology is required. And autonomous vehicles has more safety as well as security required, which is achieving the local environment of the vehicle, also the external environment of the vehicle, as we see here from GPS or other networks or databases used between different OEMs or tier ones between vehicles and has been uh, handled dynamically when the vehicle is driving. So in this, we need more safety and security of like ISO 26261, 21434 and several safety standards to be followed during development of the each ECU or each part of this vehicle, which is more important. And we will discuss about these details in upcoming videos based on the request from different users. And I just here included levels of ADAS systems. So what kind of autonomous driving levels we have currently as a standard in automotive industry from 0 to 5. Here you can easily understand what does it mean of ADAS system level 0, level 1, level 2, level 3, level 4, level 5. Coming to level 0 to 2, we have no automation for level 0, so driver has more control on the vehicle. And coming to level 1, driver assistance, just have some driving support, autonomous driving support from car electronics, but it just supports still driver needs to control the vehicle on his own driving skills. Coming to partial automation, kind of a, for example, I would say cruise control with some adaptive cruise control techniques and some braking techniques has been used in level 2 where driver need a minimum intervention when the system alerts the driver to take over the control of the vehicle. For suppose there is an environmental issue or there is a limitation in finding or understanding the vehicle environment or outside environment, the control unit gives the alert to driver to take back the control and drive himself. Coming to conditional automation level 3, and most 50% of the driving is or parking is covered by vehicle intelligence, and maybe around 30-40% of the driving to be still with the local driver. And coming to high automation, almost all 80% of the driving dynamics are controlled by a vehicle intelligence, and maybe some intervention is required at the worst case scenarios by the driver. Coming to full automation, there is no driver required, and the vehicle itself can understand the environment and the internal instances of the vehicle stability and dynamics are understandable and controlled by vehicle electronics itself, and no driver intervention is required. That's where we are seeing nowadays several driverless cars on roads and has delivering several um, user friendly commutations, I would say. Of course they are not still 100% into the market or on road, still it's under research and development, I would say. And I hope you understand this slide better. And of course, if you would like to get more interesting topics related to this automotive embedded systems and or any other latest technologies or safety or cyber security, system engineering, and software development methods, etc. I would request you to like, subscribe, and comment with the topics you are interested. And yes, stay connected. And here we discuss more details in future about future of automotive industry. Thank you for watching this video. Stay connected. Bye.